All right, so we're back for Support Vector Machine Part 2. I think in the last lecture, we kind of talked about how the objective of the Support Vector Machine came about. Like we step by step derive the background idea. And the idea was that we wanted to maximize the margin subjected to that all our labels are correct, right? Not only correct, at least greater than one. So so the idea is like if we can simply solve this, then we would be able to find the line that essentially separates the red and the blue points. Okay, so now in part two, we're going to continue and see if we can convert this objective, this objective into the kernelized version, right? So it's kernel SVM instead. Well, just like LDA PCA, the simplest way is simply convert it for every single x, map it to phi of x. Now, this works every single time if you have a finite dimension feature map. So if you have a polynomial, like a feature map of 3, 4, 5 functions, so that's not bad. Like you can do that. And then you just solve this objective exactly the same way you would solve support vector machine. However, most of the time, if you end up using an infinite dimension, the question is how do we then convert this objective so that you can deal with infinite dimension? Okay. Now the strategy is pretty simple. This right here is what we call the primal objective. Once we convert this into a dual objective, then it turns out that these becomes kernel functions, right? And in kernel functions, then we can solve it. Okay, so everything we learn from constraint optimization would then carry over. So the strategy, right? We convert the primal objective into the dual objective, and then the kernel matrix emerges. That's what's going to happen. And this essentially allows us to ignore the fact that this could be infinite dimension. Okay, so let's go over how we can accomplish this from primal to dual. Now, if you have been following along up till this point, the pattern is very, very simple. The pattern that we do every single time is we take the objective and then we convert it into matrix vector format. Converting this just makes life so much easier. So you really want to be good at doing this conversion. Now, this right here is equivalent to W transpose times W, right? So I just copied this down. The second portion over here, this is just gamma. So this is really summation of gamma I. Now, summation of gamma I is just gamma 1, gamma 2, gamma 3, basically just adding them together, which is equivalent to dot product with a one vector. Notice how if you just take all the gammas, dot them with a vector of ones, that's equivalent to adding all the gammas together. So this is converted into this here, red to red. And the blue portion, notice how you have x, which is each x is a vector. So we separate them out x1, x2, x3. And then gamma I and yi are scalars. So what we end up having is y, gamma 1, gamma 2. So this is a vector of gammas. And this is a matrix of y, where the y elements are the diagonal. Right? Notice how if you multiply this out, you end up getting a vector that's gamma 1, y1, gamma 2, y2, so on and so forth. And then when you multiply by x, we get the whole thing back together. Okay, so this blue portion is essentially the same as the blue portion here, right? And this right here, you may recognize, is simply the X transpose matrix. We're going to call this matrix capital Y, and we're going to call this the same as this, gamma. Okay, so that's just a vector gamma. And lastly, the green portion, right? You notice how the second portion, then over here, when you multiply it out, becomes this here, right? And then the last portion, if you multiply gamma and y here, then you have the gamma and the y. So the green portion is when you multiply them together. Okay, so for the last green portion, well, b is a constant, so we can just pull b out, and then it's simply gamma 1 times y1, gamma 2 times y2, gamma 3, so on and so forth. So you can see this is y transpose, and this is gamma vector again. So now that we have all these written out, you can clearly see that this right here is simply w transpose w. We're going to call this the 1 vector, and this right here is gamma vector. Okay, so 1 times gamma. That's how we end up getting this. Here's w times x transpose. See, w times x transpose times the y matrix times gamma. Okay, so that's this whole thing is turned into this here. And very lastly, b times y transpose and gamma, y transpose gamma. So now we have converted this. We have now converted into the matrix vector format. And once we convert this, all right, once we convert this, we can actually take it another step further. We can simply calculate for the solution. If we want to calculate for the solution, then we just take the derivative and set it to 0. So if you take the derivative and set it to 0, this right here just becomes w. Hopefully you remember your derivative. We're taking derivative with respect to w, okay? So that becomes w. This right here doesn't have w, so that cancels out. This right here, well, w goes away, so you only keep this. And this right here doesn't have w, so that cancels out. So the result of derivative for this is equal to this. And we can also set this to 0. So set the derivative to 0. So we know the optimal solution. The optimal solution is simply x transpose times y and times gamma. So the only problem here, right, is that we don't know gamma. So implying that if you know gamma, all the problems solved, right? But finding gamma is not necessarily an easy problem. And over here, if we take a derivative with respect to w, but b is also something you want to know. So we can take a derivative with respect to b as well. And it turns out that b just goes away, so you have this condition is equal to 0. So now we essentially have this. This is a condition that must be true, and we have this condition, right? So we know the optimum w given x. Now, if we want to kernelize this, then the optimum w would then be phi transpose y gamma. Okay, so as long as we know gamma, right? As long as we know gamma, then we essentially can solve the optimal solution. Remember, w is the same as a function. We're trying to find the optimal function. Um, so what are we doing? Yes, that's right. Um, so if we know the gamma, the key here is as long as we know gamma. Now we're going to continue. So as I was saying, we have the primal, and now that we know the optimal. Remember when we are converting from the primal to the dual, what we do is we find the optimal solution, right, for only w without the gamma, and then we plug it back into the Lagrangian. So if we plug the optimal w back into the Lagrangian, so this will be this square, right? Because it's w times w squared right here, w times w squared. So I just multiplied w times itself. So this right here is w transpose times w. Okay, and now I plug w here as well, right? Because there's a w here. So I plug that in, and I keep this portion the same, but I plug w in here, and I can keep this the same. Now remember when we took the derivative, with respect to b, it says that this has to be true, right? Has to be true. If y transpose gamma is 0, then we know that y transpose gamma has to be 0. So this is supposed to be 0, right? Which simplifies our dual into this objective. So here we have dual. So basically, that's our dual. Now, once we have dual, remember the dual is the opposite. So primal is minimization, the dual is maximization. So now you're trying to maximize this, subjected to the fact that this part is equal to 0 and that gamma is greater than 0. Now, why is gamma greater than 0? Well, that is because when we were solving the primal, right? When we're solving the primal, there's this thing called the KKT condition. Remember KKT condition, which has 4 conditions. Let's see if we can go show you the KKT condition. Was it here? Did I lose it? KKT condition. Where's the KKT condition? Let's go back. Let's see if we can find it. 4220 lectures. Spin lectures. Where's the KKT condition? Constraint optimization. Here we go. So remember what we learned in the constraint optimization. The KKT condition, look at the dual feasibility. Number 3, the dual feasibility says that gamma has to be greater than or equal to 0, right? This is where I got that from. That is always part of it. If you have an inequality, the gamma, let's see. Yeah, if you have an inequality, did I lose it? Okay, give me 1 second. So in the dual, because the dual is the variable now, right? And due to the dual feasibility, it says that this has always be true. Therefore, when you're solving the dual feasibility has to be included. Anyways, the point is now you have a constraint optimization problem, and you're essentially trying to solve this, right? This right here can be solved also with the KKT condition. You can solve this, but this turned out to be pretty simple to be solved using gradient descent. So yeah, you can actually just use gradient descent to solve this, and that's how I solved it. Right? So at this point, you notice that when we have this here, right? This part is x times x transpose. Now, if we kernelize it, it becomes phi times phi transpose. Then over here it becomes k, right? So the real objective is k here, and that allows you to actually solve this maximization problem, right? Now remember, this is maximization. So if you're solving gradient descent, you need to do the opposite. You need to do gradient ascent. So it's going up instead of going down. Right? So the goal here, right, before you're trying to solve W, but now you're just trying to solve for gamma. Okay? So once you solve for gamma, then the problem is solved. Because remember previously, when we set the derivative of W to 0, we know the optimal W. And when we convert the optimal W, the X portion, into the feature map, then the feature map looks like this, implying that the optimal function is equal to this. So this part allows us to essentially solve for gamma. Once we know gamma, then we know the optimal function and optimal W that we're looking for. Okay. So after knowing remember the optimal W is a point in RKHS, which is equivalent to the function. So it implies that then we would know the function to perform classification. If we plug at x, then the whole output will either give us 1 or -1, right? So what is this f of x? We use the reproducing property. So plugging this in as the f, so this is f star, and then inner product phi x, right? Remember this right here is the reproducing property. Therefore, if we multiply this out, that's equivalent to putting x into f star. Now, after this, phi transpose is simply phi 1, phi 2, phi 3, all the way to phi n. So this right here is every single sample times this. Now, if you remember from the LDA lecture, this is equivalent to the KX matrix. Well, it's not a matrix. It's a single row, essentially. It's a single row. Okay, resulting in a classifier that looks like this. Okay, so f of x is equal to this. So if you, classify, we'll call it a classifier of x. So if you plug x in, it will either be blue or red, 1 or -1. Okay, so that's how it works. Now, um, this is I actually programmed this kernel SVM for you and showed you guys that if you just run regular SVM, if you remember, SVM tries to draw the line, right? It tries to draw a line such that it separates the two classes the best possible, right? But however you draw the line, there's no way you can draw a single line that perfectly separates them. We're going to have some spillovers that's going to fall to the other side. That's because you simply can't draw a line for this. However, if you were to project the data, right, from the data space into RKHS, right, RKH. So the points in here, right, the data in here are in a curve space. So what's happening is you are drawing a straight line here. So you're drawing a straight line, but drawing a straight line is equivalent to drawing a curved line in the original space. So what happened here is if I just run regular SVM, then it's going to try to draw a line. But if I draw a straight line in a curved space, then in the original space, the straight line looks like a curve, right? Therefore, in this particular case, it's essentially finding uh, uh, it's finding like the midpoint that allows you to distinguish the two classes. Okay. Now I gave you guys the code here. You can take a look. I showed you guys the code. So let me see. Yeah. So what did I do here? What did I do? I have the function. So the function is 1/2 lambda transpose y lambda. Now remember, I use lambda instead of gamma. I should have used gamma instead, but whatever. And then plus u mp dot transpose y. Oh, I see. I basically do the square of this because I want to push this with gradient descent. I want this to be as small as possible. That's why I have the square. Okay. And then over here, MP transpose O. O is a vector of ones. So I see. So it wants this vector of ones times, well, I say lambda, but it's really gamma, and is trying to minimize this as well. Yeah. So basically, if you remember the lecture I taught on constraint optimization, you can't just do gradient descent directly on the Lagrangian. You need to play around with the Lagrangian, especially with uh, the equality constraint. So over here we have an equality constraint, which is this times gamma is supposed to be 0, right? So I made sure I do the square, so it's always trying to push this value towards 0. So this is how I basically achieved it. Now it is also possible to do a closed form solution, but for this particular case, it was easy enough, so I did the gradient descent. So this is how I did it. Now what I want you to do is pick a very simple example like this right here, and essentially see if you could yourself write your own version of kernel SVM as well as SVM. Okay, I'll see you in the next lecture.